Hello, I'm Rebecca Lewington. Welcome to our podcast. Everything Micron makes is a nanoscale miracle, but high bandwidth memory stacks, pun intended, multiple miracles to make the fastest memory on the planet, used when nothing else matters but speed. Now, I've been around semiconductors longer than I care to reveal, and I still think HBM is amazing. I want to share that amazement with you, so I've enlisted the expert help of Akshay Singh, who leads the R&D team in Taiwan that makes this remarkable technology possible. Akshay, thanks so much for joining me.
Thank you for having me on, Rebecca. Pleased to be speaking with you.
Oh, good. Well, first of all, tell us a bit about yourself. What's your background and what's your current role?
Sure. So my name is Akshay Singh. I'm a Vice President of Advanced Packaging Technology Development at Micron, and I lead a global organization, and our responsibility is to deliver advanced memory packaging solutions for our products. Some of my responsibilities include technology strategy and execution, supporting Micron's cost competitiveness objectives, manage our innovation agenda, establish R&D partnerships and university relationships. I joined Micron as a materials engineer about 15 years ago now. Time flies. And since then, I've continued to take on roles with increasing responsibility in the areas of package development, package design, and integration. Excellent. And this has also given me a lot of opportunities to visit a lot of Micron's global sites, as well as sites of our customers and vendors. And today I'm speaking to you from Taiwan, which is our packaging R&D site. And prior to Micron, I was in the Silicon Valley working in a startup on electroactive polymer materials.
Wow, so you're the right guy for this interview. Excellent. So first of all, what is advanced packaging? I mean, I suspect a number of people don't actually really understand what packaging is in terms of semiconductors. So
that's right. No, that's a great question. So you're right. Before we talk about advanced packaging, let's talk about what a package is and then maybe what packaging is. So in the simplest terms, if you open up, do tear down of a mobile phone or a hard disk drive, a gaming card, or a tablet, you'll see these. First of all, you'll see this green circuit board, motherboard, and then you'll see a lot of little black rectangles that are attached to it. And this is essentially what is called a package. And there's a lot going on inside, but the package is basically serving a few important functions. First of all, it protects the semiconductor chip that's inside of it. And it connects this chip to the circuit board that allows this device to then communicate with the system. And then it dissipates heat and also adds some other functionalities. Now, different steps that are involved in putting this protective structure together or putting this package together is called this discipline of packaging. And in advanced packaging, we used some advanced interconnects like copper pillars, through silicon vias, or what are referred to as TSVs, redistribution layers, and various heterogeneous integration schemes. And high bandwidth memory, or HBM, uses some of these advanced packaging technologies.
Okay, so let's start with TSVs. What is a TSV, and why are we using them for HBM?
Great question. So TSV is through silicon via. As the name describes, it is this interconnect. It's an electrical interconnect that goes through the silicon, and it connects the front side metallization on the device to the back side. So it goes all the way through. And this is a TSV provides the shortest path to connect the front side to the back side. And it is also used for, it also delivers low latency and high performance. In a product like HBM, where you use a lot of silicon layers or a lot of device layers, it allows you to connect all these layers vertically along the Z dimension or in 3D, as opposed to a wire bonding technology, where you have to have all these IOs only around the periphery of the chip to make the connection. TSVs allow you to make the connection all across the silicon and all the way through the stack. So that's why you use TSVs in HBM.
Right, and which is you said something there that we should talk about, is that it's not just a normal chip package has one chip in it. HBM has many. So
That's right.
why?
Right. Yeah. So we talked about TSVs and multiple chips inside of HBM. So to describe a little more, there can be 4 or 8 DRAM chips inside of HBM, and they're on top of what is called an interface chip, an interface layer, and all these connections are made through these TSVs. And Micron has a long history, a 20+ year history with TSV technology. In fact, several innovations and thousands of patents in this area. We productized TSV with hybrid memory cube and also with DDR 3D stacks. In HBM, we are actually using 35% smaller TSVs. So versus what we used for HMC or DDR. And these TSVs are actually they're quite small. As a frame of reference, they are about a 1/20th of a dimension of human hair thickness, or the diameter of the human hair. So you have to use several thousands of them to make these connections, because this is a high performance memory, and you have a very wide data bus, and so you need a lot of TSVs to make these connections.
Right, the high bandwidth comes from having a lot of parallel connections, which means thousands of TSVs to carry the data, but not just to carry data, right? TSVs are there to do other functions.
That's right. TSVs carry data through the chip. It allows you to stack in a 3D fashion, right? Because as I described earlier, you cannot make a connection from one layer to the next layer through with wire bond, where you have to be essentially connected at the edges. So
right.
So they serve as a high performance data path.
Right. Yes, if you were trying to make edge connections between 8 dies, it would be kind of ridiculous, wouldn't it?
It would be a lot of wires, and we do that in NAND, but the number of IOs are very limited. I mean, we're talking a few orders of magnitude less IOs in that case with wire bond.
I want to go back to something you said about size just now. You said these things were small, but compared to the size of an actual DRAM cell, the capacitor DRAM cell, they're actually enormous, aren't they?
That's true.
What challenges does that bring?
That's right. Yeah. So TSVs, you're right. In comparison to a DRAM, capacitor, they're several orders of magnitude larger, and so you have to be careful how you place them or where you place them in the device, because they create thermomechanical stresses, and so you have to design them in a way where it doesn't influence the performance of the device, but allows you to still make the connections that you need to make from that device.
Right. So once you've got a single wafer with TSVs in it, what's next?
Right. So so we talked about TSVs. In HBM, this die stacking actually is quite unique. And what I mean by that is, I talked about HMC and DDR, which also use TSVs. In that case, we do stacking on what is called a chip on substrate. So you have this interposer or a substrate layer, and then you stack one chip at a time on top of it. In case of HBM, you do this stacking on a wafer. So it's called a chip on wafer. And all your testing, as opposed to one device tested in a singulated form on a substrate, in the case of HBM, you're doing testing on a full wafer. So you have this you have this interface wafer with 8 DRAM stacks and along this whole wafer, and that's what you do testing on. Subsequent to that, you do simulation of the wafer and turn this wafer into these memory cubes, which is what then goes to the customer.
Okay, and I think we missed a step because before you can't just you started talking about it, but you can't just stack up 8 wafers because, well, for one thing, they'd be about that thick. So you've got to do something. You've got to do something to those wafers before you can cut them up and before you can stack them. Could you tell us a bit more about that?
That's right. Yeah. So we first of all, you form TSVs in the wafer, right? In the DRAM wafer and the interface wafer. And these TSVs themselves, there are different ways to form them in most of these high-end devices, and definitely in the case of HBM, we form TSVs in what's called a via middle. So what that means is you first form, you do the front end of the line processing, and then you form the TSVs, which subsequently is followed by back end of the line or metallization process. So that is step one. Via formation is step one. Now, after these vias are formed, these wafers are then go into sorting or probe to then identify which ones are good die and which ones are bad die, because for stacking, you want to stack known good die. So the first step, once these wafers have TSVs in them and they go through sorting, the very first step is you put copper micro bumps on the front side of the wafers. And these essentially will act as pillars that will make the connection to the subsequent die. Mm-hmm. So these micro bumps, they go on top of the TSVs, but on the front side of the wafer. And then you flip the wafer, and to your point, you have to reveal the TSVs. So you're going to start grinding these wafers from the back. You're going to start thinning them. So a wafer that starts with roughly 750 or 775 microns will then be ground down to about 50 microns, which is when these TSVs get revealed. And so once you reveal the TSVs, then you put what is called a pad, essentially, or underbump metallization UBM pad on the backside. And now you have a wafer with a TSV that has pillar on the front and a pad on the back. So you have this ability to make the connection all through the silicon. And now your wafer is ready. So you do that for all your DRAM wafers, and you also do that for your interface die. And at this stage, these wafers are thinner than half the thickness of a paper.
Which is amazing. How do you handle something that thin without it just curling up or breaking or just getting lost?
Right. Yeah. No. And there is a lot of technology involved in that too. You're absolutely right. Thin wafers can curl up. They can break. So after you put these pillars on the front side, before you grind them down, you're going to do what is called a bonding step. And this is part of wafer support system, where you take a carrier wafer and you take this DRAM wafer and you bond it to the carrier wafer. And then you start back grinding. So after back grind, when the wafer becomes about 50 microns thick, it doesn't curl up because it is supported by this carrier wafer. So that's how you handle a thin wafer on the front side.
So you've got to make one of these wafers and then put the bumps on the back, bumps on the front, turn it over, stick it to a carrier. Grind it down, put the bumps on it, stick it to a carrier, then cut it up. So you've now got millions of these little postage stamp floppy things, and which you then have to stack up on the interface wafer to get the finished stacks. Wow.
That's right.
Are we done? Are we done now?
Right. Well, not yet. So now you have your DRAM wafer and your interface wafer. And what you do is you have to now first debond this wafer. So the wafer that you had bonded, this thin wafer that you have bonded, you have to first then debond it, and you put it on a film frame carrier. And then Right, and then you start dicing it, because each of these DRAM have to be separated, because you're going to pick each one of them, and then you're going to start stacking them onto the interface layer. So you have to transfer it from this carrier wafer onto what is called a film frame carrier, and then you have to dice them, and now you're going to start stacking them. So just like thin wafer handling is challenging, you have to design specific tools, and you have to have certain thin die handling capability and die attach capability in order to start building these stacks.
Sometimes I wish this wasn't a podcast, because this must be amazing visually. You've got a wafer with hundreds of these stacks being built up by automatic tools. It's astonishing.
That's right. That's right.
And how did we get so good at this? You mentioned something called hybrid memory cube earlier. I'm pretty sure most people won't know what that is. Could you say some more about that?
So Micron has a rich history with TSV technology, as I mentioned earlier. We've been doing this for about 20 years, and about a decade ago is when with HMC and DDR is when we brought this technology into products, roughly 2012, 2013 timeframe. So not quite a decade. We have thousands of patents. We have very, very talented people, both here in Taiwan, in the US, and all over the world. So there is a lot of competency that we have in the company, and we partner with a lot of our vendors, and this is how we innovate and have brought this technology to HBM.
Right. So all it takes is a few decades, a few tens of thousands of talented people, and accumulated wisdom of millions of hours of research and development. No problem at all.
That's right.
Now, we're still not quite done, are we? Because of the final package that a customer actually installs in a computing system isn't just our work, is it? It includes somebody else's work.
Yes, that's right. You're right. With HBM, it's HBM is part of what is called an in-package memory solution. So what that means is you have a logic layer, which could be something like a GPU, and this high bandwidth memory, all sitting inside what is called a system in package, SIP. And in order to make that SIP, what you do is, a memory supplier like Micron would make HBM, and then this would go to an integrator, and the integrator then uses something called a silicon interposer, and on the silicon interposer you integrate a GPU, and you put these HBMs, these little tiles around the GPU, and this whole subassembly then goes on top of an organic substrate, and it's covered with a thermal lid, because these things they run very high bandwidth. There's a lot of heat generated, so you have a heat sink on the top, and now this is your product, the system in package that will then go onto a graphics card. So right. Yes, that's when you are actually done in terms of making this.
Well, that's amazing. So just to finish off, Akshay, what's next for you? What's next for advanced packaging? What's next for you personally?
Well, advanced packaging, first of all, it's such a growing area of importance as we move forward. So, of course, there is generations of HBM itself. So you have to keep innovating and keep driving, higher and higher bandwidth, lower and lower power. And there are a lot of challenges associated with that. But beyond that, with what is going on in the industry, with bringing logic and memory more closer to each other, there are several integration schemes that are coming up, broadly captured under the umbrella of what is called heterogeneous integration. So there is a lot of innovation to come in this space, and this is a fascinating field with a lot of multiple disciplines that you need in order to create these solutions. So we are excited about this. Of course, as a packaging engineer, super excited to be part of this kind of time frame in this semiconductor field. and we continue to invest and create solutions, that hopefully will delight our customers. So that's what we're shooting for.
I can't wait. If you don't mind, I'll put you on the calendar to have this chat in a couple of years' time, and every couple of years until we retire. Akshay, thank you so much for joining me. This has been absolutely amazing. Really appreciate it.
Thank you, Rebecca. It was my pleasure.